Hello everyone, this is Aditya and today we'll discuss functions in single variable in the form of a deep one shot, and in this way we'll discuss questions also. So please do like, share, subscribe my channel, and now let's get it started. So what all we cover in this lecture? Let's see. We will cover Rolle's theorem. We will cover Rolle's theorem. We will cover MVT, mean value theorem, Lagrange mean value theorem. We'll cover generalized or Cauchy mean value theorem. We'll cover Taylor series in single variable, obviously, first of all, and then we will come to Maclaurin, right? So let's start with Rolle's first of all, right? Okay. And most importantly, we will solve the questions also, right? So let's start. Rolle's theorem. So what is it? Let's see. For example, if you have a function f of x is equal to y, right? Or simply say y is equal to f of x, right? And what is a single variable function? Means the y is dependent upon x, right? It is dependent upon single variable. So that is why it is said a function in a single variable, right? Okay. So what are the conditions to satisfy Rolle's theorem? Well, let's see. For example, you have a function and you are evaluated this function in the interval x belongs to closed a to b, right? Okay. So what is its significance? Let's see. So fx must be continuous in closed a to b, right? Okay. And fx must be, what is the meaning of continuous? Means it should not break at any instant, right? At any value of x between a to b, right? And x must be differentiable between open a to b, right? Open a to b, okay? And f at a must be equal to f at b, right? Okay. So why do I am telling all these conditions? Let's see. So let's draw such kind of function. Well, let me draw it. So this is our f at a, and it is given it is equal to f at b. Okay, f at b, right? Suppose this is your a and this is your b, right? Okay, this is point a, this is point b, right? F a comma fb, sorry, a comma fa, and this b comma fb, right? So what are the conditions that you can draw this graph? Well, let's see. The first way is you can draw it like this, somewhat like this. The second way is you can draw it like this, a constant function. And the third way is you can draw it like this, right? There's no other possibility, right? And why do I am telling all these possibilities? Well, when you are drawing this graph, then you see that at in this case, this and this, where you are where the function is not a constant function, in that case what is happening is you are getting a peak over here, right? And in this case also you are getting a peak, but in the case of a constant function you're not getting a peak, but you can see that it is a constant function, right? So what does it tell? Let's see. So let's see with a different case, I mean this one, where you are getting a peak. So observe that in this case the function is rising, it's increasing till a particular value, suppose this, and then it is gradually decreasing, right? Since fa is equal to fb, so it means that the function will increase till a certain value and then will start decreasing. Or maybe there's a possibility you can draw it like this also, maybe this and like this, right? You can do it like this also, so you can get multiple peaks in this case, right? Okay, but for simplicity we will look into the basic idea, right? Okay, so just observe that this is the peak, so it corresponds to some value of x at x is equal to c, right? Okay, this is the case. So why do I am telling all this? Well, the Rolle's theorem states that if a function satisfies such conditions, this, and this, then it means that there exists a C which belongs to A to B such that f dash at C is equal to 0, right? And observe that since it is the maximum value, so at that point the tangent is 0, means that slope of the tangent is 0, which means the derivative at that point will be 0, right? You can interpret from the graph, because the function is increasing then decreasing, so there is a point where the function becomes 0, the derivative of the function becomes 0, right? Over here f dash x, oh, just a minute, let me turn off. Yeah, f dash at x is greater than 0. Here f dash at x is less than 0. So here f dash at x is equal to 0 at this point. And here point is C, right? I hope you are understanding it. Okay. Let's see the proof also for better understanding. Well, you observe that f at C plus delta x, right, minus f at C will be less than equal to 0, right? Since C is since at C the function is attaining its maximum value, right? So what does it tell? It tells that wait. So this is your equation 1. Okay. Now just see, f dash at C plus delta x minus f dash at C divided by delta x will be greater than 0 for delta x less than 0. I hope you are understanding it. Means you are going towards left, right? Towards f dash x is greater than 0, right? And when you are seeing f of C plus delta x minus f at C by delta x, it will less than equal to 0 for delta x greater than 0, right? We are understanding it. And notice that this is f dash at C only, and this is f dash at C only, right? Okay. It is the LHL and this is the RHL. This is the LHL and this is the RHL, right? Or rather I should say not RHL, it is LHD and this is RHD, right? Okay. Which means f dash C is greater than equal to 0 and f dash C is less than equal to 0, which implies f dash C is equal to 0, right? I hope you are understanding it. Okay. So that is the basic proof of the Rolle's theorem, and let's see some questions upon it so that the things become more clear. So let's see some questions. I have brought a question series also over here. So I hope that let's do the first one. First of all, let me change the color. Let's do this one, right? It is a bit easier for you to understand, so that is why, and rest you can solve it on your own. And let's see first of all the Rolle's question. In this you are said you have to verify the Rolle's theorem for this expression in 2 to 3. Okay. F at x is equal to x square minus 5x plus 10 for x belongs to open closed 2 to 3, right? Okay. So since it is a polynomial, so it is a continuous function and it will be differentiable, right? So you don't need to prove it. Since it is a polynomial, which implies it will be continuous plus differentiable, you can write the statements on your own. I'm not discussing about all that. Okay. And you observe that f at a is equal to f at 2 is equal to 2 into 2 square minus 5 into 2 plus 10 is equal to 4, and f at 3 is equal to f at b is equal to f at 3 is equal to 3 square minus 5 into 3 plus 10, and it is equal to 4. You can check it, right? Okay. Which means it is satisfying the condition of Rolle's theorem. So there must be a point that exists, right? In that case, f dash of x is equal to what? It will be 2x minus 5, right? 2x minus 5 is equal to 0, and evaluate it at x is equal to c. So you get c is equal to 5 by 2, right? Okay. And observe that c belongs to 2 comma 3, right? Maybe I did not wrote it over there. um no, I have written. Okay. And observe that in this question, yeah, that's it. So that means there exists a point C is equal to 5 by 2 where the Rolle's theorem is satisfying, right? Okay. Hence Rolle's theorem verified. And now let's see next question. Let's see. I will do third one and you have to practice the second one, okay? Because they both are similar. So let's see the third one. Okay. So let me change the color. So let's see. Third one, you're given fx is equal to x to the power 13, x to the power 13 plus 7x cube plus 7x cube minus 5 minus 5 and is equal to 0, and we have to prove that it has only one real root. Okay. So for the time being, you can assume that fx is equal to x to the power 13 plus 7x cube minus 5 has two roots, alpha and beta, has two real roots, alpha and beta, right? Just for instance, because if you prove that there can't be two real roots, then you can gradually prove that there can't be 3, 4 and more roots, right? So there will be only two possibilities, that there is no real root or one real root, and we can check it further, right? So let's first of all see what is it. Okay, so just observe that it is a polynomial again, so it is continuous and differentiable, so I'm not writing it to that. And observe that f at alpha will be equal to f at beta will be equal to 0, since it is the root. They both are the roots, right? So just differentiate this expression f dash at x is equal to 13x to the power 12 plus 7x square 3 into, right? So you get 13x to the power 12 plus 21x square. It must be equal to 0 at x is equal to c. And you get c square common. You get 13c to the power 10 plus 21 equal to 0. And observe that there's a possibility that c can be 0, but that will a particular case, right? So we can't just take that case and solve, right? So that is why you have to take a general case. So you get c to the power 10 is equal to negative 12 by negative 21 by 13. And observe that it is c raised to the power 10, means it is c raised to some even power. So it can't be a negative number. So it implies there exists no c belonging to alpha to beta, right? Which means there exists no real root. There exists no two real roots, right? Or more than it. So there is only one possibility, that there are only two possibility, that there can be no real root or there can be one real root. So how do we check it now? Let's see. Let's substitute f at 1. You get 1 plus 1 plus 7, yeah, 1 plus 7 minus 5, 1 plus 7 minus 5, and you get it equal to 3, right? And you use f at 0 is equal to negative 5, yeah, which means the function is going somewhat like this. At some point between 0 to 1, the function is gradually negative over here, and then it is increasing, right? Okay, so it means it is cutting the x-axis at least at one point, at max at one point, right? So it has one real root, right? Exactly one time it is cutting the x-axis, so it has one real root. Okay, I hope you understood it. And let's see what's the next question. Well, prove that between 2 points. You will do it on your own. Sorry, you will do this on your own. Just assume this as the function and then differentiate and put c. You will get this expression, right? Okay. And now let's move on to the next topic, Lagrange mean value theorem, and rest I hope you can do in rules, right? There is nothing much to it. Okay, so now moving on to, but before moving to Lagrange mean value theorem, I will teach you all theta h form. What is it? Let's see. Well, let's see what is theta h form. For example, you draw a graph, okay? A to B, right? And you choose a point over here, for example C, right? Okay, now you have to represent C in terms of A and B, right? So how you will represent it? Well, suppose H is equal to B minus A, means the width, you can say, right? So you can say C is equal to A plus B minus A, but it is wrong because you will end up getting C is equal to B. So to manipulate this, you put theta over here. Wait, why did I use the theta over here? Well, let's see. Theta is equal to A plus theta into B minus A. What is the limits of theta? Theta is belonging from 0 to 1 in the open braces, not the closed. So what is its significance? Well, when you substitute theta as 0, means forcibly you are substituting theta as 0, you get C is equal to A. And when you substitute theta as 1, you get C is equal to B. You can check it, right? And these are the extreme boundary points, right? And in that case, you can't put the C as 0 and 1 since you are using the open braces, but we are forcefully trying to put theta as 0 and 1, and we are getting A to B. We are getting the boundary limits, which means between 0 to 1 we will get the value of C, right? I hope you are understanding. Between theta from 0 to 1 you will get this region, right? Excluding A and B, right? Okay, so you can write C is equal to A plus theta H, right? This is just a way to represent things, nothing more. Okay, it makes the calculation easy. Now let's move to LMVT. So let me write over here, this is the first topic, okay, and this is going to be our second topic, right? Okay, LMVT means Lagrange mean value theorem. What does it state? Let's see. Okay, it is very simple. The function must be continuous in closed A to B and must be differentiable in open A to B. That's the condition. Okay, I hope you got this, right? So if these two conditions are satisfying, then there exists a C belonging to A to B such that f dash at C is equal to f at B minus f at A by B minus A, right? This is the condition. Okay, I hope you are getting it, and if you are not getting it, we will see it using a question also. But first of all, let's approach it graphically. Let me use different sketch for it. Okay, so this is the condition, not the condition, but the graph. Maybe this is A, this is B, right? This is this point and this is this point, right? Okay, this is your f at A and this is your f at B. There is no condition f A is equal to fb, right? Understand it. So you get somewhat like this, maybe, right? And now just join this and this point, right? Okay, and name it as AB, right? What is the slope of AB? M of AB is equal to f at B minus f at A by B minus A, right? Is it correct? Yeah. So what is the basic idea of Lagrange mean value theorem is that you will try to find a point C such that the slope of that point is equal to the slope of the line AB, right? Right? So what is the slope of the point C? It will be f dash at C, right? So you will try to find a point C, f dash at C, such that the slope of that at that point is equal to slope of that line AB is equal to f at B minus f at A by B minus A. This is the basic idea of Lagrange mean value theorem geometrically and graphically, right? Okay. There is one more method you can use to prove this theorem, but I don't believe in that much because it is very much like rote learning sort of thing. But let's see. You assume a function phi of x is equal to f at x minus f at b minus f at a by b minus a into x. And in this case, you observe that phi at a will be equal to phi at b. You can solve it, right? So in this you will apply Rolle's theorem and you will differentiate phi of x and you will get this expression only, right? But I don't believe much into this because if you know the graphical approach it will be very easy, right? But for knowledge purpose you should know this, right? Okay. Maybe I should write it over here that phi of A is equal to phi of B, right? Okay. Now let's see a question on LMVT so that the things become more easy. Let's see, is there any question? So verify. Let's start with the 8th question, 8th first part. Rest you will do on your own, right? Okay. Verify LMVT for the following case, right? Okay. We are seeing the 8th first question and it states f at x is equal to x minus 1, x minus 2, x minus 3 for right? Okay. So let's see the question. Fx is equal to this. Okay. So you have to solve, you have to verify Lagrange mean by theorem on it. Okay. Let's see. Just see it is a polynomial again. So it is differentiable and continuous. You don't need to check it, right? And you can just multiply this stuff. You get x square minus 3x plus 2 into x square minus 3. You get x cube minus 3x square plus 2x minus 3x square plus 9x minus 6, right? And just observe that you get x cube minus 6 6 x square. I guess I'm doing the calculations right, I hope, right? Okay. Plus 11x minus 6. If my calculations are wrong at some point, just bear with it because maybe there's chance that while recording the things may not define. That is why. So just observe it, and if there's a problem then please let me know, I will clear it. Okay. So now you find f dash at c. Just differentiate it and then put c, right? Get 3c square minus 12c plus 11. And notice that it will be equal to f at b. What is f at b? F at 4 minus f at 0 by 4 minus 0. This is f at b. This is f at a. This is b. This is a, right? I hope you are understanding it. So you get 3c square minus 12c plus 11 is equal to, when you substitute 4, what do you get? You substitute 4, you get 3 into 2 into 1, you get 6. 6 minus, you put 0, you get negative 1 into negative 2, it will become 2 into negative 3, it will become negative 6. So you get negative 6, right? Divided by 4, which is equal to negative 3, right? I hope you are understanding it. So you get 3c square, you get 3c square minus 12c plus 14 is equal to 0. And you solve for c, you get 12 plus minus root 144 minus 4 into 14 into 3, and you get what expression do you get? I hope that maybe I made a calculation error over here. Yeah, it will be plus 3, right? So that was the issue, sorry. So when you bring 3 over here, you get 8 plus 8 is equal to 0, right? Okay. So now let's see, c is equal to 12 plus minus root, just Brahmagupta formula, right? We sometimes say Brahmagupta formula, we sometimes say Sridharacharyaji's formula, and somewhat like that. 144 minus 4 into 3 into 8 by 6, right? So you get c is equal to 2 plus minus root 144 minus 12. What is 12 into 8? It is equal to 96. And 144, 96, when we subtract, you get simply 48, right? I guess I'm doing the calculations right. Please bear with me if it is wrong, right? And you get so why do I'm writing it? It will be 48, right? By 6. Okay. So c is equal to 2 plus minus 48 by 36, and you can solve it very easily. 4 by 3, you get c is equal to 2 plus minus 2 by root 3, right? And observe that these two quantities, these two values of c is indeed belonging to 0 comma 4. So there, so I had said, as in the case of Rolle's theorem you can get multiple c's, in the case of LMVT also you can get multiple c's. So that is why these both c are valid, right? Hence proved. Hence Lagrange mean value theorem is verified. Let's see another question which maybe we can solve. Well, let's do 10th one, right? This is somewhat a new type of question. So we won't do first of all 10th one, we'll do first of all we will do 9th one, right? Because 9th first part and rest you will do on your own, right? I will tell you all 9th first and second part, because these two will make some sort of problem for you, right? So I will discuss these two, right? So in LMVT only I will tell you all one thing, that you know that f of b minus f at a by b minus a is equal to f dash at c, right? Now use theta h form. You get f at b minus f at a is equal to h into f dash of what was c? C was a plus theta h. A plus theta h, right? So you get f at b is equal to f at a plus h into f dash of a plus theta h, right? And this is very much helpful result. Why? We will see it, right? Let's see. Just remember it. Okay. So let's see. The question number 9th, first part, right? Okay. Let's see. It states that we have to prove that using mean value theorem, that is the Lagrange mean value theorem in this case, you have to prove that, show that this expression, okay. So basically you need to prove that x minus 1 upon x is less than log of x is less than x minus 1. You need to prove it for x greater than 0. Okay, I guess it is greater than 0 or greater than 1. I have to see it. Yeah, it should be greater than 1 only, because in that case log will be right. Okay, greater than 1. Okay, so how do we solve it? Well, let's see. X belongs to closed 1 to x, right? Okay, just assume it. So it means a is equal to 1 and b is equal to x, right? So just use f of x equal to log x. Okay, we have used fx is equal to log x. Okay, so you get fx is equal to log x, right? Okay, so simply you know that f at b is equal to f at a plus h into f dash of a plus theta h hota hai. We know this. Okay, so what does it mean? It means that f at b is equal to f at a plus h into what I am writing. Yeah, what is b? B is equal to x is equal to function at 1 plus h. H is b minus a. What is the derivative of log x? It will be 1 upon x. You put 1 plus theta into x minus 1, right? 1 plus theta into x minus 1. Basically you derivate, you get 1 upon x and you put a plus theta h. A is equal to 1 and theta is theta and h is x minus 1, right? Okay, so you get log of x is equal to, what is log of 1? It is simply 0 plus x minus 1 upon 1 plus theta x minus 1, right? Okay, so you get log of x is equal to x minus 1 upon 1 plus theta x minus 1. Okay, and you know that theta belongs to 0 to 1, right? So forcefully set theta is equal to 0, because see, when you forcefully put theta as 0, you get the minimum denominator, and when you get the minimum denominator you get the maximum value of the function, which means log x will be less than equal to this quantity, because you won't get less than equal to, since theta was not in the domain, since 0 was not in the domain of theta, right? That's why. So this is your first expression, and you put theta as 1, you get the maximum denominator, so you get the minimum value of log x. Just substitute, you will get this expression, right? So combining, you get x minus 1 upon x is this expression, hence proved, right? And just notice, for example, if you would have a negative sign, for example, you would have got x minus 1 by 1 plus, instead of 1 plus, you would having 1 minus theta of x minus 1. So in that case, what would the criteria? In that case, theta is equal to 0 would not yield the maximum but the minimum value, and theta equal to 1 would yield the maximum value, since when you substitute 0, you get the maximum value of the denominator, and when you substitute theta as 1, you get the minimum value of the denominator, right? Okay, just note this, just some logics, and everything will be clear, right? So now you will do this question, cos x1. I hope that no, you can't do this cos x1, because it is related to Taylor series right now, so we won't worry about it. You will do this fifth one on your own, right? On your own, right? Okay. And the 10th one also you can do it. Let's see how to do 10th one, then we will proceed to our next topic of Cauchy mean value theorem, or generalized mean value theorem, right? So you have to prove that the cube root of 28, it lies between 3 plus 1 upon 28 to 3 plus 1 upon 27, right? Okay. So in this case, what you have to do is you have to apply some logics, and you will be able to figure out the things, right? So how you will do it, let's see. Okay. So in this case, just you are not given any function. So in this, you have to assume a function. Since it is cube root of something, so you will assume cube root of x as a function, right? This is the basic idea, that you will assume this function only, right? You can't approach using any other function, right? So it is a basic idea. Just it is probably the case you assume the middle function as the function by which you have to work out the expressions, right? Okay. So basically, and you will assume that x goes from 27 to x. Why so? Because you see, you get a 3 plus some expression, and over here also 3 plus some expression. So which means that it will be better if you use such approach, right? Because if you put f at 27, you will get 3, right? So that is why. Okay. So now just apply LMVT, you get f at x will be equal to f at 27. I am not writing the formula again, you know it. Plus x minus 27 into f dash of 27 plus theta into x minus 27, right? Okay. And since you are evaluating it at 28, I will directly substitute it over here. Is equal to, what is 27? 28 minus 27, it is equal to 1. And what is the derivative of x cube? X to the power 1 by 3. X to the power 1 by 3, when you derivate it, you get 1 by 3, x to the power 2 by 3, right? You can solve it. It is very simple result, okay? Plus 1 upon 3 into x plus 27 plus theta into 1, because 28 minus 27 is still 1, raised to the power 2 by 3, right? So f at 21, it is equal to cube root of 28 is equal to 3. What is the cube root of 27? It is 3, right? Plus 1 upon 3 into 27 plus theta raised to the power 2 by 3, right? You put theta as 0. Since theta belongs to 0 to 1, you forcefully putting theta as 0, so that you get the minimum denominator and you get the maximum value of this function. Of this value, it will be less than 3 plus 1 by 3 into 27 to the power 2 by 3, right? So you get cube root of 28 is less than 3 plus 1 upon 3 into, what is this? Cube root of it is 9, and it was 27. So you proved the first expression, right? Okay. So you get cube root of 28 is less than 3 plus 1 upon 27, right? You proved this thing. Okay. Now what you have to prove? You have to prove that it is less than 3 plus 1 upon 28. Let's see how you will prove it. Cube root of 28 is equal to 3 plus 1 upon 3 into 27 plus theta raised to the power 1 upon 3, 2 upon 3, right? Now put theta is equal to 1. So you get cube root of 28 is equal to 3 plus 1 upon 3 into root 20. Let me write it clearly. 28 2 by 3, right? And this is the minimum possible value, right? Okay. This is the minimum value, right? Of this expression. Okay. But this is not similar to what we are asked. So how we will solve it? Well, let's see. You can write this expression as 27 raised to the power 1 by 3 into 28 raised to the power 2 by 3, right? Or just leave this. You all can simply do it like this. What is the expression asked? It is asked 3 plus 1 upon 28, right? So just compare these two. Well, if it will be greater than, if this expression is greater than, then you can clearly say that cube root 28 will be greater than this expression also, right? Since if A is greater than B and B is greater than C, which implies A will be surely greater than C, right? Okay. So you solve it, you get 1 upon 3 into 28 raised to the power 2 by 3 will be greater than 1 by 28. So you get 28 by 28 raised to the power 2 by 3 will be greater than 3. So you get 28 cube root will be greater than 3, which means 28 will be greater than 27. Yeah, this is correct. Which means this expression is greater than this expression. So it means that cube root of 28 is greater than 3 plus 1 by 28, which implies that cube root of 28, it lies between 3 plus 1 by 28 and 3 plus 1 by 27, right? That's the expression. Okay, done. So let's move on to the Cauchy's mean-value theorem now. And yeah, you can solve this expression also. Let's see how we solve it. We will do 11th also. Wait. Let's see. So in this you have to prove that now let's solve the question number 10 and I mean 11. So there was some disturbance. Now it's fine. So we had to prove that sine of, let's see what was the question, I don't remember. So let's see. Sine of x minus sine of y is less than equal to x minus y. Okay, so you need to prove this and consequently prove this experiment. Okay. We will see it. Sine of x minus sine of y is this quantity, right? Okay. So what we can do is now, what you can do is that you can assume fx as sine of x, right? Simply assume this expression, right? Now apply Lagrange theorem. Lagrange mean value theorem, sorry. F at b minus f at a upon b minus a. Here b is equal to y, a is equal to x, right? Or you can say opposite also, x and y, since whatever the case is, right? So f at x minus f at y by x minus y is equal to f dash at c, right? Okay. So you get sine of x minus sine of y is equal to, what's the derivative of sine x? It will be equal to cos x, right? It was equal to x minus y into cos of c. Just take mod both sides as given in the question, and this is the thing. And notice that so we get sine of x minus sine of y is equal to x minus y into cos of c. Well, let's see. Cos of c, it lies between negative 1 to 1, and notice that the mod will lie between 0 to 1, right? Okay. So just substitute this expression and you get that sine of x minus sine of y will be less than equal to x minus y, since the maximum value of cos c is 1, right? So you can just say this thing, right? Okay. So I hope you understood that how we will solve it. And the consequent part, it states that consequently prove that this expression is greater than this. You can prove it using LMVT, right? You don't need to worry about it. Okay. Again, you can use like we did in this case, right? Just apply that thing. It is this question. Okay. So now I don't think so that there's any question left. So let's move on to Cauchy's mean value theorem. Okay. So just a minute. I hope there is no disturbance, right? Cauchy mean value theorem. What is it? For example, it is applicable for two functions, right? For example, if you have two function fx and gx, right? So in that case, and you are given that they both are continuous and differentiable in a to b, right? Open a to b is they are continuous, and in closed and in open a to b they are differentiable, right? So in such case, right? So in such case, there exists a C belonging to A comma B such that f dash at C by g dash of C is equal to f at B minus f at A by g at B minus g at A, right? And notice that in this case that g dash of x should not be equal to 0, right? Because if it will be 0, then the result will be undefined, right? It is simple, right? How do you approach it graphically? First we will see graphical approach, and then we will move on to the approach that we generally use, like some sort of rote learning kind of thing, right? And after that I will tell you something really amazing result, and which will blow your mind, really. I'm not joking, it is true. You can just remember one formula, and from that you can derive any formula in this chapter, right? And it will be really amazing. Let's see how. But first of all, let's see it graphically. Graphically it will be like this, right? Okay, this is x, this is your y. Okay, so just see, this is your a and this is your b, right? And suppose this is a, this is this function, this is this function, right? And suppose this is like this. Okay, just assume for the time being this is a and b, right? You are joining these two, right? Okay, so what is this? Well, you are using x is equal to g of t and y is equal to f at t, right? Why? You will see it later. Okay, and t belongs to closed a to b, right? Okay, okay. So what's next? Well, let's see. Well, what will be a? A will be g of a comma g of comma f of a, right? And simply this will be f of g of b comma f of b, right? Okay, this will be expression. Okay, so when you join these two expressions, what you get? The slope of AB, it will be equal to g, it will be equal to the f at b minus f at a by g at b minus g at a, right? Is this expression correct? Okay. So similarly, as you did in the Lagrange-Mean theorem, you will find a slope, a point on the graph such that the tangent to the graph to that point is parallel to AB, right? So suppose this is the point C, right? Okay. So what is it? You get dy by dx at x is equal to C. You get dy by dt by dx by dt. You get f dash of t by g dash of t at t is equal to C. You get f dash at C by g dash at C is equal to f at b minus f at a by g at b minus g at a, right? So that is the expression. So this is a graphical way to prove this thing. And if you are asked mathematically, then in that case you can apply again phi function f at x minus f at b minus f at b minus f at a by g at b minus g at a into g of x minus g of a, right? So why you are doing this? Since in this case you can apply again Rolle's theorem, right? But I am not much into the favor of this, since it is more sort of rote learning kind, because there are very less logics for this. Okay, so I prefer the graphical approach more, right? Okay. So I had said that I will tell you one formula, and using that you can approach all the three formulae very easily. So let's see it. Well, you know Cauchy mean value theorem. It states that f at b minus f at a upon g at b minus g at a is equal to f dash at c by g dash at c. So now this is Cauchy's mean value theorem, right? So in this, what you can do is you can assume gx as a linear function x, right? Okay, so when you assume this, you get f at b minus f at a upon, when you substitute it as a linear function, which implies g at b will be equal to b and g at a will be equal to a, right? And what's the derivative of g dash x? It will be equal to 1, right? So you get b minus a is equal to f dash at c, right? So you get LMVT, right? Okay, and you substitute fa equal to fb, you get f dash of c is equal to 0, since fb minus fa will be 0, right? So what you have done is that you have approached from CMVT, you approach to LMVT, and you approach to Rolle's mean value theorem, right? Or Rolle's theorem, right? Simply Rolle's theorem, right? Rolle's, right? In this, to approach this, you substitute g of x is equal to x, and in this you substitute fa equal to fb. So you just need to remember that f at b minus f at a upon g of b minus g at a is equal to simply f dash at c by g dash of c, and in this you substitute g of x as x, you approach to LMVT, and then you substitute fa equal to fb, you approach to Rolle's. It's so simple. Just remember one formula and you can approach all the three methods. So I hope you understood this. So let's see some question on this also, and then we will move on to the next expression. I mean the next topic of Taylor's theorem. So let's see the questions of Cauchy mean value theorem also, and then we will move to the next topic. Let's see the 12th first part, right? Let me change the color. So you get this expression, you have to solve this thing, right? So let's see how do we solve it, and let's see. Okay, 12th first part, and in this case, so let's see, in this case we are given that fx is equal to square root of x, I guess. Let's see what was given. Fx is equal to square root of x and gx is equal to 1 upon root x. Okay, let's see. Fx is equal to root x and gx is equal to 1 by root x, and in the interval 1 to 3, right? This is the question. So it is simple, and it is very simple actually. Just what you can do is f of 3 minus f at 1 upon g at 3 minus g at 1. You have to apply a Cauchy mean method, nothing else. Okay, f dash at c by g dash of c. Notice this is continuous in the interval 1 to 3, right? And is a differentiable also, right? You don't need to check, right? Even if you check, you get the same result. Okay, so you get root 3 minus root 1 upon root 3 minus 1 is equal to f dash of c. It is equal to 1 by 2 root x into negative 2 x to the power 3 by 2, right? You can solve it, right? It is simple, right? I don't think so that I need to tell this. It will be equal to root 3 into root 3 minus 1 by 1 minus root 3 is equal to this, and this cancels, and you get negative x, right? You get this expression. So you get x is equal to root 3, right? And obviously x is equal to c, so c is equal to root 3, and yeah, it is correct. You get the c as in between this expression, right? I don't know, I don't remember I wrote over there or not. That c should belong to, yeah, it is correct. Many people write it like this also. The c, they write it like that epsilon. So that is also fine. It is just a number, nothing else. Okay. Okay. So now let's see what else can be done. Well, almost we have done all the parts. Now we are just left with the Taylor's theorem. Let's do the Taylor's theorem also, and then we will do some questions, and then we'll wind up. Okay, so I don't think so I have a space over there, so I will write Taylor's theorem over here, right? So let me create a page. I need 2 pages for that, 2 to 3. So let me write over here Taylor's theorem, right? And okay, now it's fine. Well, coming to the next topic of Taylor's theorem. It is, I guess, the fourth topic, Taylor's theorem, or Taylor's expansion, or Taylor's formula, whatever you want to say. And it is simplest generalization of MVT, right? Somewhat like that. So what we will do in this is we will assume a function that a function fx such that it is n plus 1 at time differentiable. Don't ask me right now why, you will see it later, okay? And now you will define a polynomial. You will define a polynomial Pn of x, right? And it will be such that, means it is n, so it will be nth degree, obviously. And you have defined it such that Pn of x naught is equal to f at x naught is equal, and Pn of ith derivative of x naught is equal to f of ith derivative of x naught, right? This is the case where I can be any value, right? Okay. So you are basically defining it like that x naught is some value, right? Okay. So just say Pn of x is equal to c naught, a general way to write a polynomial. That's it, okay? Till Cn x minus x naught to the power n, right? This is the case, okay? That is the case now, okay? And since you know this thing, right? Okay. So now you'll solve for the coefficients. Let's see how you will solve for coefficients. Let's take derivative of p of x. You get, I am not writing n right now because it takes lots of space. Let's c1 into c1 plus 2 c2 into x minus x naught till n cn x minus x naught to the power n minus 1, right? And notice that if you take the nth derivative, you get n factorial, since you get n, and you get n minus 1 into n minus 2 until 3 into 2 into 1, right? N factorial into x minus x naught to the power 0, right? You get this thing. So you get Pn of x is equal to n factorial into Cn, right? And notice that Pn of x is equal to f of nth derivative of x naught, right? That's correct. Okay. You just substitute x naught over here, right? Simply, okay? So you get Cn is equal to f of nth derivative at x naught by n factorial, right? So from this you get Ci is equal to f of ith derivative of x naught by I factorial, right? This is the case, okay. So you get Pn of x is equal to f at x naught plus f dash of x naught by 1 factorial into x minus x naught till f of nth derivative of x naught by n factorial into x minus x naught to the power n, right? And this is a polynomial, right? So basically you are converting a polynomial in terms of a function, but we have to convert a function in terms of a polynomial. So that is why we have to interchange somewhat, right? That is what is the main idea of Taylor's theorem? It is used to convert a function in terms of a polynomial, right? But here what is happening is that you are converting a polynomial to in terms of functions, right? And that is not the case, which you have to do, right? So in this case we will define a remainder term. Let's see what is its significance. Rn of x is equal to fx minus p of x, right? Just assume for the timing, right? Okay, just assume. And you are defining g of x is equal to x minus x naught raised to the power n minus 1, right? Just for the time being, assume it, right? Why we are assuming, you will understand it later, okay? And in this you are assuming that g of k at x naught will be equal to 0, right? For k is equal to suppose 0, 1 till n, right? Whatever be the case. Since it is simple, when you derivate this term and substitute x naught, you get 0, right? That's the case, okay? So, and now observe that g of n plus 1 of x naught, it will be equal to n plus 1, right? You can observe it, okay? It is very basic idea, right? N plus 1 factorial, sorry. Okay? N plus 1 factorial, okay? Now apply the Cauchy mean value theorem, right? Okay. So when you apply Cauchy mean value theorem, what you get? R of x minus r at x naught by g of x minus g of x naught is equal to r of x by g of x is equal to r dash of x, r dash of c by g dash of c, right? Okay, is this fine? Okay, c1 you can say right over here. And why it is equal to why, where is x naught disappeared? Well, let's see. When you substitute x naught over here, you get r of x naught is equal to f at x naught minus p of x naught. But we had proved that p of x naught is equal to f x x naught. So it means f x x naught minus p at x naught, it will be equal to 0, right? And when you substitute x naught over here, you again get a 0, right? I hope you are understanding that what I am saying, right? Okay. Oh, and I am sorry, it will be equal to n plus 1, right? Over here. G of x is equal to n plus 1, okay? I hope you are getting this, okay? And why I have assumed it? Well, it's just an assumption and you will see it later, okay? So r of x by g of x, you assume r dash of c1 by g dash of c1 is equal to r double dash of c2, g double dash of c2, and you can go up to r of n plus 1 at derivative of c n plus 1 by g of n plus 1 of c plus n plus 1, right? That is the case, okay? I hope you understanding it, okay? What is Rn? Well, we will see it. That is what we need to solve. It is equal to x minus x naught to the power n plus 1, right? That is the case. What is the derivative of n plus 1 at times the derivative of that quantity? Well, let's see. Of this, you can say it's psi. And what's the derivative of this expression n plus 1 at time? Well, you calculated it is equal to n plus 1 factorial. N plus 1 factorial. How? Just see, you just differentiate, you get n plus 1, you get then n. So you go till n plus 1, that it will become x minus x naught to the power 0. So it will be independent of the value of x. So you get n plus 1 factorial, right? I hope you are understanding it, okay? If you don't, then please comment me and I will tell you all, okay? So now observe that r is equal to f minus p. It was this. So r of n plus 1 is equal to f of n plus 1 at derivative of x minus p of n plus 1 at derivative of x. Notice that it was a polynomial of nth degree. So for example, if you have x square and you derivate it 3 times, you get a 0. So simply it will be also 0. Since it is a nth degree polynomial and you are derivating it n times, right? Okay. And what is f of n plus 1 of x, right? You get this expression, right? Okay. Now let's see, it was psi, so let's write psi only, okay? It will be better. So you get r of x upon x minus x naught raised to the power n plus 1 is equal to f of n plus 1 at derivative of psi by n plus 1 factorial. So you get Rn is equal to x minus x naught raised to the power n plus 1 upon n plus 1 factorial into f of n plus 1 at derivative of psi, and you can write psi in terms of theta x, but not right now. We will see it later, okay? So you get this expression, right? Okay. Now this is Lagrange remainder form, and it is like this: n plus 1 by n plus 1 factorial into f of n plus 1 derivative of psi, and you can also write it like this: x minus x naught raised to the power n plus 1 by x plus 1 factorial n plus 1 factorial f of n plus 1 derivative of x naught plus theta into x minus x naught, right? You can write it like this. So what is the significance of this remainder? Well, it is used to convert. It is earlier when you were solving, you are getting the polynomial in terms of a function, but you wanted function in terms of a polynomial. So this remainder will convert that polynomial to a function, right? So you will get a function in terms of a polynomial, and that will be very much helpful, right? So just write px was equal to, let me see what I had written. It was equal to fx minus rx, right? You can solve it. Fx minus rx, right? This is correct. Okay. And now you know that px was equal to fx naught plus x minus x naught into f dash of x naught by 1 factorial till f of any derivative of x naught by n factorial into x minus x naught to the power n, right? Now you can write pn as fx minus rx, and you can bring that rx over here plus rx, and you can write that rx as this thing plus x minus x naught, or f of n plus 1 derivative of this thing. Well, I don't think so that it is need to be written, but let's write plus theta into x minus x naught by n plus 1 factorial into x minus x naught to the power n plus 1, right? My writing is not good over here, but I hope you understood that it is simply rx. Rx is equal to f of n plus 1 derivative of this expression, that what I had written over here, right? Okay, we will see some questions on it and then we'll wind up. Okay, and just see what is Maclaurin series. Well, Maclaurin in this case, you just substitute x naught is equal to 0, and as limit x tends towards 0, x tends towards infinity of rx, it should tends towards 0. Then in this case, the Taylor's tends towards Maclaurin. Okay, that's the thing. Okay, I hope you understood. Okay, now let's see a question on it and then we will wind up. Okay, well, let's see the question. The question is, let's see the 16th one, right? 16th, by Taylor's theorem, prove that this thing. We will just see the half part. This thing. Okay. Or this is bit simpler. You can do it on your own. We will see this one because this is more likely, right, to come or some sort like that. So we will see this part, right? Okay. So let's see. Let's see the question. I hope I have space. Yeah. So let's see. It was, I guess, question number 16, and you have to prove x minus. What was that? Let me see. X. Yeah. X minus x square by 2. X minus x square by 2 is less than this quantity, and okay. X minus x square by 2 is less than log of x is less than log of 1 plus x is less than x, right? This is the expression, I guess. Okay. Yeah, this is the expression for x is greater than 0. Okay. For x greater than 0, right? Okay, so that is the basic idea, right? So how do we check it? Well, you apply fx is equal to log x, right? Log 1 plus x, and now you can f at 0, you get a log of 1, you get 0, right? Okay, so that is the thing. Okay, now what you can do is that you can apply the Taylor's now. F of x is equal to f at 0 plus x minus 0, since that is x naught is 0 over here. See, this is the x naught, x belongs to 0 to x, right? So this is the x naught and this is the x, right? So this is this quantity f dash at 0 by 1 factorial plus, and notice that since it is going till x square, right? Since it is going till x square, so I don't think so that we need to work much, right? So let's see, x minus x naught whole square by 2 factorial into f double dash of a plus theta h, you can apply, right? A plus theta h, it is simply that quantity, it is simply the remainder, right? That is the thing. So fx is equal to, what is log of 1? It is 1 plus x by, what is the derivative of log this? This will be 1 plus x, right? I hope you understood, right? Okay. And we are evaluating it at 0 plus 0, okay? Plus x square by 2 factorial. What is the derivative of 1 by x? It is equal to negative 1 upon x square, right? So negative, wait a minute. Negative 1 upon x plus 1 whole square. Evaluated x is equal to, what is a? A is equal to 0, theta x minus 0, right? Since h is equal to x minus x naught, right? Okay. So fx is equal to x minus x square by 2 factorial into 1 plus theta x whole square, right? It is equal to log x, right? Okay. Now put theta as 0. You get the x minus x square by 2 factorial expression. And notice that it is the least value. It is the minimum first value of log x. Why? Because indeed you converted a denominator to minimum. So you get the maximum expression of x square by 2 factorial. But it is a negative sign. So you are subtracting a maximum value from something. You will get the minimum value of this expression. And when you substitute and obviously you can see that since you're subtracting something in this case, so let's apply again the Taylor's theorem. So you prove this, now apply again Taylor's theorem. Fx is equal to f at 0 plus x minus 0 upon 1 factorial into f dash of a plus theta h, right? Just apply. This is indeed LMVT only. LMVT is a general case, sorry, LMVT is a special case of Taylor's, you can say like that. So f of x is equal to x into 1 plus theta x, right? This you will get, obviously. So when you substitute theta as 0, you get the minimum value. So you get the minimum value, you get log x, minimum value of the denominator, so you get the maximum value of the expression. Log x will be less than x. So you end up getting x minus x square by 2 factorial is less than log x, and this is less than x, right? I hope you understood it, right? Rest you can do on your own, okay? So what's the next thing which you can do? Let's see. Well, let's do one more question and then we'll wind up, okay? We've done this. You will solve this on your own with the same logic. Now we will do this one and then we will wind up, okay? You have to find log of x at about point A, okay? Okay. Let's, I need one more page. It was, I guess, 17 question. Fx is equal to log x, and it was still fourth, right? So means you have to go till fourth derivative, right? Okay. That's just something at about a is equal to 1. Okay, let's see. So what you get is that you find first derivative, you get 1 upon x. You find the second derivative, you get negative 1 upon x square. Find the third, you get negative 2 upon x cube. You find the fourth, you get negative 6 by x to the power 4, right? Somewhat like that. Okay. And now you get f at x can be written as f at a plus h, right? F at, or simply x naught plus this x naught plus x minus x naught, right? Like this. So you get f at 1 plus x minus x minus 1, right? So simply just open it. F at 1 plus x minus 1 upon 1 factorial into f dash of 1 plus x minus 1 by 2 factorial in this whole square f double dash of 2 plus x minus 1 whole square whole cube by 3 factorial to f triple dash of 1, it will be 1, sorry, plus since you are going till the fourth expression, so you will simply x minus 1 to the power 4 by 4 factorial into f of fourth derivative at 1, right? Simply just do it like this, okay? So what is the f at 1? Log of 1 is 0, so you get this 0 plus x minus 1 by 1 you substitute, you get 1, and when you substitute 1 over here, you get negative 1. So you get negative x minus 1 whole square by 2 factorial, and when you substitute over here negative, you get over here third, it will become positive, it will become plus 2 by 1 into x minus 1 whole cube, right? I hope if there is some calculation error, you will figure it out, and I'm just telling all the method that how you can do it, okay? Maybe I make some calculation error, so kindly bear with it. To the power 4 upon 4 factorial, right? Okay. So you get f at x is equal to this thing, x minus 1 minus x minus 1 whole square by 2 plus x minus 1 whole cube by 6 by 3 actually minus 4 into 6, x minus 1 to the power 4 by 4, right? Now put 1.1, you get 0.1 plus minus 0.1 whole square by 2 plus 0.1 whole cube by 3 minus 0.1 whole to the power 4 upon 4, and you can solve it, right? So this is how you solve about when you are asked to find about a particular value, right? So I hope I have covered everything which is possible in this chapter, and I hope that it would help you all. So thanks a lot for watching it, and take care, bye bye, and please do one thing, and please do subscribe my channel, and please support me. Thanks a lot, bye bye, take care.